Welcome to Invisible Engines, Advances in Distributed, Parallel, and Cluster Computing. In this episode, the focus is on the latest breakthroughs that drive the digital backbone of our world. Key advances in speed, reliability, and sustainability for large-scale computing will be explored, including a highlight on Li et al.'s SmartFill algorithm for optimal scheduling. The discussion centers on cloud, AI, scientific, and blockchain systems, with insights curated from 84 papers published between September 1st and September 15th, 2025. Here is the roadmap for today's presentation. The session begins by unpacking the foundational concepts and driving challenges of distributed, parallel, and cluster computing. Attention then shifts to 6 key research themes that are shaping the future of the field. 3 seminal papers that push the boundaries of current knowledge will be spotlighted. The methodologies behind these advances and their critical findings will be synthesized. And the presentation concludes with a look ahead to future directions and emerging opportunities. Distributed, parallel, and cluster computing is the science of making many computers work together as one powerful system. Tasks are split across multiple machines to enhance both computational power and resilience. Parallelism enables faster results by dividing workloads among processors. Cluster computing connects hundreds or thousands of computers, so they act as a unified engine. These approaches form the foundation of today's digital infrastructure, powering artificial intelligence, cloud applications, scientific modeling, and blockchain ledgers. The first major theme is smarter resource management and scheduling, which focuses on optimizing efficiency in real-world workloads. Li et al. Introduced the SmartFill algorithm, designed for optimal job scheduling. Labra presents dynamic resource allocation, tailored for large language models. These solutions address the challenge of unpredictable, non-linear job speedups, where adding more resources does not always yield proportional performance gains. The overarching goal is to maximize throughput while minimizing delays and resource waste. A key technical concept here is the concave speedup function, where returns diminish as more resources are added. Theme 2 centers on fault tolerance and instant recovery, ensuring systems can bounce back from failures almost immediately. Flash recovery, developed by Zhang et al., enables checkpoint-free, rapid recovery for AI clusters. Mycroft traces complex dependency chains to identify root causes of failure. These systems are capable of detecting and recovering from faults in real time, with recovery times that do not scale with the size of the cluster. The technical breakthrough of checkpoint-free recovery allows system state to be rebuilt from lives rather than relying on full snapshots. The third theme addresses energy efficiency and sustainability, with a focus on greener computing for data centers and AI workloads. Voltana LLM introduces adaptive frequency scaling to reduce the power requirements of large language model serving. Masso accelerates AI inference while also saving energy. The sustainability of cloud computing has become a research priority, prompting the development of new models that balance performance with environmental impact. Energy-efficient algorithms are now critical tools for reducing both operational costs and the carbon footprint of digital infrastructure. Theme 4 examines advances in AI serving, security, and efficient data movement. LiquidGem by Hu et al. Achieves rapid quantized matrix multiplication for large language models, significantly improving inference speed. Achior introduces a 2-round consensus protocol that enhances blockchain security. The STZ framework delivers high-speed streaming compression, supporting near-real-time data analysis. Machine learning techniques are increasingly utilized for fraud detection in distributed ledgers. Efficient data handling remains essential to enable breakthroughs in both scientific research and artificial intelligence. Key findings from September's research highlight significant progress and impact across the field. The smart fill algorithm by Li et al. Provides unified, optimal scheduling for a variety of workloads. Flash recovery achieves cluster-wide AI recovery in under 2 minutes. Voltana LLM demonstrates up to 36% greater energy efficiency in AI serving. Acori's consensus protocol enables fast and secure transactions for distributed ledgers. The STZ streaming compression framework increases throughput by a factor of 7, facilitating real-time handling of massive datasets. Recent breakthroughs have been engineered using a range of advanced methodologies. Mathematical modeling is used to achieve provable optimization, as demonstrated by Li et al. And Akior. Hardware-software co-design unlocks new performance levels, as seen in Liquid Gem M and IMPIR. Large-scale experimental evaluations are conducted on live clusters, exemplified by Mycroft and Pyramid AI. Machine learning methods power anomaly and fraud detection, notably in projects like detecting rug pulls and CloudFormer. Novel algorithms and protocols are being developed to solve foundational problems, with contributions from works such as Bodega and new consensus approaches. A selected paper, Optimal Parallel Scheduling under Concave Speedup Functions by Li et al., resolves a decades-old challenge in job scheduling. The paper introduces the Consistent Derivative Ratio, or CDR rule, which guides efficient resource allocation. The smart fill algorithm dynamically allocates resources to maximize system efficiency, generalizing the water filling approach to accommodate arbitrary speedup functions. The impact of this work is significant, enabling practical and optimal scheduling in real-world cloud and edge systems, regardless of workload diversity and unpredictability. The next highlighted paper is Flash Recovery for Large-Scale AI Training by Zhang et al. This work delivers checkpoint-free, near-instant recovery for clusters training large language models. The system detects failures in real time and restarts tasks in a manner that is independent of cluster scale. Recovery for even the largest clusters, such as those with up to 4,800 GPUs, is achieved in only 150 seconds. This advancement saves substantial time, financial resources, and computational power, setting the new standard for resilience in distributed AI training environments. Another featured work is Liquid Gem, High-Performance LLM Serving by Hu et al., which introduces hardware-efficient W4A8 gem kernels for rapid and accurate serving of large language models. The liquid quant method allows for near-instant dequantization, requiring minimal computational overhead. A fine-grained pipeline is implemented on GPUs, overlapping loading, dequantization, and computation without software synchronization. Liquid Gem achieves up to a 2.9-fold speedup compared to previous state-of-the-art approaches, enabling more users to be served with less hardware and reduced energy consumption. Looking ahead, several future directions and opportunities are emerging in the field. Deeper integration of machine learning is anticipated to enable predictive and autonomous system management. Hardware-software co-design is expected to become a central pillar of system architecture as traditional chip designs reach their limits. Sustainability is moving from an afterthought to a fundamental consideration in both algorithm and infrastructure design. At the same time, debugging and root cause analysis are becoming increasingly complex as systems grow in scale and heterogeneity. Security, privacy, and trust continue to be ever-present challenges that must be addressed as distributed systems evolve. This presentation was synthesized using advanced AI tools and human expertise. Summarization and narrative construction were powered by GPT 4.1 from OpenAI. Text-to-speech synthesis and image generation were also managed by OpenAI's multimedia capabilities. All synthesized content underwent review by human experts to ensure accuracy and clarity. Listeners are reminded that some oversights may remain, and original references should be consulted for complete technical details. All referenced papers are cited throughout this presentation. In this podcast, the latest breakthroughs in computer science and AI are delivered directly from the arXiv preprint server. From neural networks to quantum computing, complex research is simplified so listeners can stay ahead of the curve. Whether you are a developer, researcher, or technology enthusiast, AI Frontiers provides daily updates to keep you informed. Thank you for listening. If you enjoyed this episode, please subscribe for daily updates. More cutting-edge AI insights will be shared tomorrow. Disclaimer, this video uses arXiv preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.